Most of our work today is going to be over section 1.3, but it might not be the same way that you've talked about complex numbers in the past. What we need to do is we need to talk about the term complex numbers versus real numbers versus imaginary numbers. Because there are several different ways we classify numbers in this class and in math in general. Now, before we get going, we start talking about these things called imaginary numbers, which is a terrible name. We have a hard enough time getting people interested in math without calling something imaginary. I want to remind you of something that I alluded to earlier in this class, and that is imaginary numbers have nothing to do with domain. Today I'm going to break a rule, and I'm going to take the square root of a negative number, which I told you is not allowed. I'm going to take the square root of a negative though. And when I do that, it's going to lead to these things called imaginary numbers, but we still are not going to let imaginary numbers enter our thinking when we're talking about domain. So, even though we will square root negative numbers today, the domain of f of x equals the square root of x is still 0 to infinity. The quick reason for that, and it might not sit that well with you, but there is a reason for it, and that is when we're talking about the domain of a function, we want to know what numbers we can plug in a function and get a real y value out, not an imaginary y value. So this is not going to change, everyone. We still are not allowed to just plug a negative number in here as far as the domain goes, but later I am going to bring that rule in a different context and take the square root of a negative. So that's where imaginary numbers come into play. Imaginary numbers come into play when we are forced to square root a negative while solving for x. That's where they're going to come into play, everyone. When we're forced to take the square root of a negative while solving for x. Solving for x is an old game in mathematics. I mean, as soon as you learned about the variable x, people had you solving for x. They gave you problems that looked like this, and they told you to solve it for x, and you divided both sides by 2, and you said x equals 4. Or they gave you something like this, x squared equals 9. You applied the square root property, and you got plus or minus 3. But what's going to happen is at some point we are going to be forced to apply the square root property when there's a negative number over here, and that's where we're going to get imaginary numbers. What happens when we solve for x here? That's what's going to happen. We're going to answer that question. So that's what an imaginary number is. It's a number that comes about when we're forced to take the square root of a negative number. Real numbers are all your numbers that are not imaginary. This includes 0, positives, negatives, fractions, horrible decimals. So, what are some real numbers? Well, anything that doesn't involve the square root of a negative. So, 6 is a real number, negative 4 is a real number, 0 is a real number, 1/2 is, negative 3/7 is. What are some that are a little bit worse that are still real numbers? Pi is a real number, good. How about a square root of a positive number? Is that a real number still? Yeah, those are all real numbers. As long as you're not taking the square root of a negative, you're talking about real numbers. So they can get really, really unfortunate and nasty. And what makes them a real number? They appear on the number line. Now, pi is a nasty decimal that goes on forever and ever and ever. It's like 3 point something, I don't know. So I can't tell you exactly where it is on this crude drawing, but I can tell you that pi is right about there. I can find it on there. I know that it exists somewhere between 3 and 4 on the number line. So even though it's a nasty decimal, I know it's on there. But you can't find something like that, the square root of negative 11 on the real number line. You cannot find that there. It doesn't make any sense to say that's between 3 and 4, or even between negative 3 and negative 4. It's just not on that number line. That's what makes it an imaginary number. Not the fact that it's not important in mathematics, not the fact that it doesn't exist at all. What makes it an imaginary number is it is not on this number line. It is a number that you really can't say is bigger than smaller than any number on that number line. Square root of a negative. We use imaginary numbers so often that the most important imaginary number is the square root of negative 1. And most of you already know this. If you didn't know it already, you did your pre-work. What's our symbol that we use to indicate the square root of negative 1? I. Good. We use a lowercase I. I usually use a little stripped I. But a lowercase I is going to be the symbol for the square root of negative 1. Now, that means that if I equals the square root of negative 1, then I squared is the square root of negative 1 squared, or negative 1. Anyone in here ever seen the movie Superbad? It's a movie about these high school kids trying to buy beer. The reason I bring that up is because I'm tired of talking about math. No, the reason I bring that up is because there's a math class scene where the students are not paying attention, but you'll, if you listen to the teacher droning on and on in the background, this is actually what he's talking about. So if you watch that movie again, listen, you'll hear him talking, getting all excited and jazzed about the fact that I is the square root of negative 1 and I squared is negative 1. So that's kind of fun. So if an imaginary number is the square root of a negative, we can kind of expand that to saying, so imaginary may have I in it, which is the square root of negative 1. So when I said before that imaginary numbers have the square root of a negative in it, you might not actually physically see that square root of a negative because you might see I in there instead. In fact, that's what you'll see more often, is you'll see I in there. So that lets me write this. Complex numbers are all the numbers. So if someone says, I'm thinking of a number, you don't even need to ask them if it's a complex number, because whether it's real or imaginary, if it's a number, it's a complex number. Complex number means all the numbers. I'm going to underline that 2 more times, because it's all the numbers, real or imaginary. Any number you can think of, no matter how nasty, no matter how long the decimal, no matter how many square roots of negatives are involved, it's considered a complex number, because that's all the numbers ever. But we need a general form to write that, so our general form for any complex number is a plus bi. What that is, everyone, and this is kind of nasty at first, the first time you see that, so don't let this discourage you. What that means is any number you can think of, real or imaginary, can be written in this form, where perhaps a or b is 0. So, think of a number that we all like, 4. It's an easy number to work with. Is 4 a complex number, by the way?
Yes.
How do you know that?
It's part of a real number set.
Because every number, yeah, it's part of the real number set, and every number is a complex number, but you could write 4 like this. Because no matter how imaginary those imaginary numbers are, they still follow the rule that if you multiply them by 0, they go away. So this is how you could write the number 4. Now, most people are not going to do this, just in general. Like with someone, if you ask like a first grader to write down all the numbers 1 through 10, they're not going to go, well, I'm going to write it like this. That's not going to happen. But that is a valid way to write the number 4. And it's valid to write the number I as this. So that's what I mean when I say we can write any number we want in this form, but sometimes you leave off a part by writing it as 0. Oh, the number 1,782 is the same thing as 1,782 plus 0i. It just doesn't have that imaginary part on it, so we don't bother to write that. Okay. So let's summarize here. Here's how we classify numbers. If anyone ever asks you if a number is a complex number, you say yes, because a complex number is every number ever. Nothing is left out. A real number is any number that does not have the I or the square root of a negative in it. In other words, you can write a real number as a plus 0i. You just don't have this part here, and you just write the number part there that doesn't have the I or the square root of the negative. A non-real complex number is something like this, where b does not equal 0. So a non-real complex number is just saying it has the imaginary component in it. And pure imaginary means you don't have the part in front. You don't have the a. Now I'm going to show you an example of what I mean by this. I want you to have this in your notes, of course, but I'm going to show you what I mean by this. Classifying numbers. Here's 13i, everyone. It's a number. Is it a complex number? Yeah, it's a complex number. Because every number is a complex number. Is it a real number? No. Why do you say it's not a real number? Because it's got 9. Okay. Is it a non-real complex number? Is it not real?
Yes.
Yeah. Another way to read this is just saying it's not real. Yeah, because it's got the I in it. So this is also a non-real complex number. Is it also pure imaginary because it doesn't have the A part in front? Yeah, you see this A plus BI? It's just the BI part. So that's why we say it is also pure imaginary. So what would something like just 15 be? What would 15 be?
Be a complex real number.
It'd be a complex number because every number is complex, agreed? Is 15 also real? Yeah. So this would be a complex number and a real number. And how about this? 2 plus 3i. Is that a complex number? You don't even need to look up. Is that a complex number?
Yeah.
Yeah. It is also a non-real complex number because it's got the I in it. It's not real because it has the I, and it's not pure imaginary because it has that 2 plus in front, or the 2 in front. All right. So the natural question to ask at this point, which I've already started to allude to, but here's what we ask. Why do we need I? Why do we have this? Why am I bothering you with this today? All right. I will show up when we find the zeros of some equation. And I wrote the word zeros here. And it's important if you're taking notes, you're looking at that later, that you notice that I wrote the word zero, not the number zero. I didn't put a circle, apostrophe S. I will show up when we find the zeros of some equation. And what do I mean when I say zeros? These are the numbers you can plug in for X, so you get a result, a Y value of 0. See, the word zero, Z-E-R-O, refers to the list of numbers, which might just be one number, but the list of numbers that you can plug in for X and make the entire equation go to 0. That's what they are. So if someone says, find the zeros, that's what they're asking you to do. Like this. When someone asks me to find the zero, what they're asking me is they're asking this. What X value could you plug in there so you get an answer of 0? That's what the question is. So the way we would solve that is we'd set the equation equal to 0 and solve for X. That's how you find the zeros. You set the equation equal to 0 and you solve for X. So 4x minus 20 equals 0, 4x equals 20, x equals 5. 5 is the 0 of that equation. It is the number you can plug into that equation to get a result of 0. Here's the exact same question written in a different way. Solve 4x minus 20 equals 0. It's the exact same question as find the 0 of f of x equals 4x minus 20. It's just a different way of asking you to do it. We are not alarmed by that in a math class because of this idea. Everyone, what's 2 plus 3? What do you get if you add 2 and 3? What's the sum of 2 and 3? I just asked the exact same question 3 different ways. It happens all the time in mathematics that we can ask the same thing in different ways. The same thing here. Find the 0 of f of x equals 4x minus 20, or solve 4x minus 20 equals 0. It's okay. The answer here is also 5. So, throughout chapter 3, we will find the zeros in equations with x's to larger powers. We'll we'll see equations that maybe have an x squared in them, or x cubed in them, or an x to the fourth in them, and we'll have to find the zeros of those equations, which of course is more complicated. The higher your x power gets, sometimes the more complicated it can be to find your zeros. Find the zeros. Find the zeros of that equation. That would be something that's a bit more tricky. It's not as easy in this one to just add the 20 to both sides and divide both sides by 4. This is a trickier problem to find the zeros. Why are we doing all this? Remember, I'm getting up to imaginary numbers here. I will show up when we find the zeros of some equations. That's what we're building up to. We're building up to finding the square root of a negative when we're trying to find zeros. So don't lose the thread here of what's happening. I know it's easy because I talk fast. How do you usually find the zeros of this? I don't want the answer yet, but how would you go about finding the zeros of this? What do you usually do? What do you think?
Factoring?
Yeah, usually someone would factor this. Exactly, well done. You would take x squared minus x minus 12 equals 0, and you'd factor it. This happens to factor as x minus 4, x plus 3. Now this, what I did right here, is making you squirm in your seat, because you never did quite like factoring. Unfortunately, this is not the main thing that we cover in this course. What they kind of expect is when you come into college algebra, you already have a pretty good grasp of factoring. So if this is something that you're struggling with, make sure you talk to Rachel and I outside of class, because we can help you with this, and we'd love to help you with this, but it's something we can't devote a lot of class time to. After you set that equal to 0, what you do is you use the zero multiplication property, that if these two things multiply to give you 0, then one of them has to be 0. So it's either the case that x minus 4 equals 0, or x plus 3 equals 0. That means either x equals 4 or x equals negative 3. These are the zeros. Those are the numbers that I am claiming that I could plug into this function and get a result of 0. I plug a 4 in there. It's going to be 16 minus 4 minus 12, which is 0. That's what was supposed to happen. I claimed that 4, the number 4, was a 0, the word 0, because the number 4 gives me a result of the number 0. Should that also happen if I plug in a negative 3? It should. Equals 9 plus 3 minus 12. It does. If anyone in here ever asks a friend for help with your math homework, and of course you're encouraged to do that, you're allowed to ask for help when you're doing your math homework. Just be aware that some people call zeros roots. So if you're asking for a friend from your cousin later, and she says, oh, you're trying to find the roots of this equation, she's not actually talking about square roots. That's just another term that sometimes people use for the zeros of an equation. So don't be alarmed if someone uses that. We're going to use zeros because I think it's more clear, and it's what our book uses. So we'll use that. But just in case you're asking for a friend, outside friend, for help, we'll just keep that in mind. All right. So let's see what happens here. Find the zeros for both f of x and g of x. What that means, what I'm thinking is this. Okay, I'll be given two equations, and I need to find the numbers I plug into them to get a result of 0. That's what I'm kind of thinking of when someone says, I'm going to give you two equations, find the zeros. I'm thinking, okay, I'm going to need to find the numbers that get plugged into these equations to give me zero. That's what I'm looking for. Now this is a fairly popular setup when finding zeros. So popular that I'm going to give you a tip about it. You see, when we're told to find the zeros, the first thing you should do is set the equation equal to zero. That's your first step, set the equation equal to zero. But then, if your equation is just two terms, x to a power and a constant, move the constant over and take, well in this case it's going to be the square root, but I'll just say the appropriate root of each side. If it was an x cubed, you'd take a cube root of both sides, but since this is going to be an x squared, we're going to take the square root of both sides. If your equation is just two terms, x to a power and a number, you move the number over to the other side, and in this case, we're going to take the square root of both sides. So right here, I'd add 16 to both sides. I'd get 16 equals x squared. Right here, I'd subtract 16 from both sides, and I get negative 16 equals x squared. Now, if I'm going to apply the square root property, if I'm going to apply the square root property here, does everyone see how I'm going to end up taking the square root of a negative? Yeah, this one's not a problem. Apply square root property. Yeah, you know, I'm terrible because all the time I'll say take the square root of both sides, but that's not really what you're doing. You're applying the square root property. It looks like you're taking the square root of both sides, but there's subtle differences. So this becomes plus or minus the 16 equals square root of x squared. This goes plus or minus the square root of negative 16, the square root of x squared. What's the square root of 16? 4. So this ends up being x equals plus or minus 4. That's two answers, everyone, plus 4 and minus 4. And this one, some of you already know the answer, but we haven't discussed it in class yet today. I know some of you know it. Let's take a break here. And we're going to take a break from this problem, not our break yet. It's too early. Now, what happens next? If you have square root of a negative number factor out a negative 1 and give it its own radical. If you have a square root of a negative number, factor out a negative 1 and give it its own radical. Just like that. Square root of negative 16 becomes a square root of 16 times negative 1, or the square root of 16 times the square root of negative 1. Why would I do that? Do we have another way to write this? How can we rewrite that? I. Square root of negative 1 equals I. So now we have the square root of 16 times I. Do we know what the square root of 16 is? 4. So we get 4i for our answer. So, when I was told to do this problem, to find the zeros of this, and I set it equal to 0, and I subtract the 16 from both sides, and I apply the square root property, The square root of negative 16 is the same thing as 4i. So this becomes x equals plus or minus 4i. That's where we're going to see imaginary numbers come up most often in this class. When we are trying to find the numbers, you can plug into a function to make it equal 0, and we're forced to take the square root of a negative. Why does this work? Squaring. What's 4 squared, everyone? 16. Careful here. What's I squared? Negative 1. 16 times negative 1 plus 16 is what?
0.
There's two numbers, negative 4i and plus 4i, that will make this thing equal 0. It just happens we need to bend the rules a little bit, and that number is a number that when squared gives you a negative result. So, what can we say? We can say this. If, I'll say the function, because we're just working with functions in this section. If the function for which you are trying to find the zeros has x to an even power, and that's going to be almost always x squared in Math 121, then there is a chance not positive, you will find the square root of a negative number and your zeros are imaginary. That's the summary, everyone. If the function for which you are trying to find the zeros, which is going to be a very common question in this chapter, find the zeros. Find the zeros. Find the numbers that you plug into this equation to get a result of 0. If the function for which you are trying to find the zeros has x to an even power, that will almost always be an x squared in this class, but technically it could happen with any even power, then there is a chance you will find the square root of a negative number during the course of that problem. One of the steps might involve a negative number, which you take the square root of, and then your zeros are going to be imaginary. All right. Let's do, okay, class, let's say we're supposed to find the zeros of these equations. No imaginary numbers here, don't worry. But if you find the zeros of this one, you do 4x minus 8 equals 0. Actually, I want to do that the other way around. Sorry, I made a mistake here. I want to do 8x minus 4, sorry. 8x minus 4 equals 0. 8x equals 4. X equals 4/8 or 1/2. That is the exact same thing as 0.5. So unless the math homework is freaking out on you and says you must enter a fraction or you must enter a decimal, it doesn't matter which one of those you put in. They probably won't let you get away though with 4/8 because that's not reduced. If you're doing this one over here, you do 6x plus 2 equals 0, 6x equals negative 2, x equals negative 2/6, which is negative 1/3. Is that the same as negative 0.33? Is negative 1/3 the same thing as negative 0.33?
Yes.
Is it close or exactly the same?
Well, you have to have the line over it, right?
You'd have to have the line to say it's repeating, agreed? Because it's actually the same thing as negative 0.3333 forever. So, if they're asking for an exact answer, they're happy with this. But they will freak out on you for that. And I don't think they have a way to put in that repeating line on the math homework, because you're going to have to use a fraction. So just be aware, everyone, that me, your math teacher, I don't really care if you use fractions or decimals as long as they're the exact same fraction in decimal, as long as they mean the exact same thing. These do not mean the same thing.
No. For the first one, you'd have to use the half, or the fraction of the decimal, but for the second one, the whole.
So only use decimals if they are exact, not approximations. All right, now find the zeros. Maybe there's just one, so find the zeros. Now there's a couple thoughts that go through my head when I see this. I'll tell you what they are so you can think about them too. I see x squared. So maybe my zeros are imaginary. When I see an x squared, I think maybe I'm going to end up with imaginary zeros. I don't know that I'm going to, but it's possible. That's the first thought I think of. And here's the more important one that people mess up. I can't just move the 8 and square root because of the 6x. Those problems I was doing before, where I just moved the number over and I applied the square root property, did not have that middle term, that 6x term. So what happens is, when you see this problem, the unfortunate confused student does this. This is what the confused student does. They set the whole thing equal to 0. They subtract the 8 from both sides. And then they think that they're allowed to apply the square root property. And that's not going to get you anywhere. That does not work. This is bad. That's no good. It's no goo either, but it's also no good. That's what the poor confused student does. Why? Because math's hard, and they forgot how to do this problem. Not their fault. Here's what the clever student does. The seasoned math student. How did we solve the other one where we had 3 terms like this?
Factor.
We factored it. By the way, are you allowed to ask Rachel or myself for help if you have trouble with factoring? Can you come see us? Of course you can. One way that I hate to see people mess up factoring is they forget that after you factor it, you have to set the individual factors equal to 0 and solve for x. Because people think you factor this as x plus 2 and x plus 4, and those people are right. But then they start thinking that 2 and 4 are their answers. But are 2 and 4 the answers? No, negative 2 and negative 4 are. They're the zeros. They're not just random answers, they're zeros. They're numbers that you could plug into the original function and get a result of 0. So, it's kind of frustrating when you see that and you say, well, Steve, the way you did that and said I would do that if I was confused, that's kind of the way I was thinking of maybe, so how am I going to keep track of all the ways I'm supposed to find zeros of different equations? Well, you're going to see these instructions a lot. Or you might even see this. where they set it equal to 0 for you. Really, they have already done your first step. Because when I see an equation, they say find the zeros, the first thing I do is set it equal to 0. So if they set it equal to 0 and say solve, they've actually already done your first step for you. Well, lines are cool. It's just move and divide. What do I mean by move and divide? I mean, if you have something like f of x equals 3x minus 28, you set it equal to 0, you move the 28 over, you divide by the 3, and you're done. Lines are awesome to find the zeros up. Quadratics are harder. Equations of that form are called quadratics. We actually learn more about that in our next section, but I don't want to drop that term without telling you what it means. Quadratics are harder than lines because they've got these 3 terms in them sometimes. So there's this one. You see, there's all these different forms that quadratics can take on. By the way, I made these up randomly, so don't try to solve these. But there's all these different forms they can take on, but the main thing to make something a quadratic, everyone, just so you don't worry about it, is this term right here is required. You need that term. These two are optional. And if you look at these, you'll notice that all of them have that x squared part in them. The other part is optional. You don't need that for it to be a quadratic. But what's tricky is knowing how to find the zeros of one of these because they all behave differently. And that's where we're going to start after our break today. So find the zeros. Now these are all called quadratics. And what makes something a quadratic is it has that x squared term in it. There's a little bit more to it than that, but we'll get into that in a later section. But these are called quadratics. And the reason I put these 3 up here is because you'll notice they're all slightly different, and that this first one, f of x, doesn't have that term with just the x. It has the x squared term and the constant. The g of x has the x squared term and the x term, but no constant. And the last one just has the x squared term. It doesn't have the x term or the constant. So if we're supposed to find the zeros, this one right here, what we'll say is, does not have that bx term, that term that was in the middle when I gave you the formula earlier for quadratic. So what we do is we move, divide, and apply square root property. So we set 3x squared plus 75 equal to 0, because that's what we always do to find zeros. We move the 75 over by subtracting 75 from both sides. This one we're not quite ready to apply the square root property yet. We have to divide by that 3 first. Get the 3 out of there. So we divide both sides by 3. And that gives me x squared equals negative 25. And I'm about to apply the square root property. Who can tell me something about my zeros right now? What kind of zeros am I going to have?
Imaginary.
They're going to be imaginary because I have a negative 25 over here. Now, this is going to be x equals plus or minus the square root of negative 25. Now, if it bothers you taking the square roots of negatives, let me just tell you this. You would take that just like you would the square root of 25, but you're also going to pick up an I. That's how it works. So you all know the square root of 25 is 5. So the square root of negative 25 is 5i. So this ends up being x equals plus or minus 5i, which means we have 2 zeros. That's actually 2 answers. I'm a big fan of the plus minus symbol because I do think it saves time. I'm all for using that plus minus whenever I can. But I will say it sometimes makes people forget that they're actually finding two answers, not just one answer. So that's the only danger of it. But we do have two answers, 5i and negative 5i. Those are the numbers you can plug into the original equation and get 0 as an answer. Look at this one right here, 4x squared minus 12x. This one does not have the c term. It doesn't have that constant at the end. So what we do here is we are going to factor out greatest common factor, which includes x. I'll show you what I mean by that. But we set this one equal to 0, 4x squared minus 12x equals 0, and you don't move anything over to the other side. You factor out the greatest common factor, which should include an x. These both have x in common. Does everyone agree with that? What else are 4 and 12 both divisible by? 4. So you pull out a 4x. Now what you have is you have two things getting multiplied to equal 0. So it's either the case that 4 times x equals 0 or x minus 3 equals 0, which means we get x equals 0 and x equals 3. Those are our two zeros. Notice with that one, I did not move anything over to the other side. You don't always move things to the other side. In fact, if you move things to the other side here, you'll lose. Okay, last one. This is the easiest one. If you only have the ax squared term, then 0 is your only 0. That sounds weird when you just hear me say that out loud. 0 is the only 0, but what I mean is there's only one number you can plug in here and get a result of 0, and that is the number 0 itself. So if you just have this, the answer is going to be 0. How does that work? Well, it works like this. You see, if you set that equal to 0, you divide both sides by 18, this goes away, and you apply the square root property, you just get plus or minus the square root of 0, which is just 0. So finding the 0 of quadratic is very possible. You just got to be aware they come in different forms. And if you start moving things over to the other side with this one, you're going to get messed up. So what did I not include? I didn't include the one that has all three terms, because that's the trickiest one. The trickiest quadratic, and remember what a quadratic is, it's something that looks like this. To find the zeros for has all three terms. Has all three of them. Factor. You could factor one of these things if it's possible. Some of these can't be factored, so if it's possible, you could factor it. Be good at it though. You could use a really cool technique called completing the square. That's how you can find the zeros. It's a technique I'm going to teach you a lot more about next time. It's pretty awesome, actually. Some people hate it, but I'll tell you why I like it later. Or, there is a special formula that can find the zeros of any quadratic I wonder what that formula is that you use to find the zeros of any quadratic. Anyone know? It's called the quadratic formula. You seen this sucker before? It's okay if you haven't. It's also okay if you have. It's called the quadratic formula. You actually hear about the quadratic formula quite a bit, and even when people don't have it memorized, they still actually remember hearing about it. What's interesting about this is it has one big job. It has one big job, and that is give the zeros of an equation of the form and several smaller jobs. There are a couple other things you can do with it, but it's amazing how often it seems to come up in mathematics when it really only has one big job, and that is find the zeros of something of this form. Now, before I go any further, let me just tell you, the A and B in this formula are not the A and B in A plus BI. We just happen to use the same letters sometimes for different things, but the A and B you see up here and here, these are not the same A and B that I was talking about earlier when I said complex numbers are A plus BI. I know that's annoying, but it's even more annoying if no one tells you that. So this formula can be used to find the zeros of a quadratic. I'm going to show you how it works right now. All right. X squared plus 3x minus 10. The instructions? Find the zeros. All right. Someone might say, hey, Steve, I can factor that for you if you want to save some time. And I'd say, that's great. I'd love to factor that. X plus 5, x minus 2 equals 0. X plus 5 equals 0. X minus 2 equals 0. Equals negative 5. X equals 2. And I'd say, thank you. Well done. Because factoring is actually easier than the quadratic formula if you don't have to, if you can see how to factor it. But the quadratic formula can also be used to find the zeros of that. And here's how it works. Yeah, question?
Does that only work factoring when you can factor it just once? Or can you go like, let's say...
So let's say someone gets this one. Let's say this is your homework problem. It says find the zeros, and you don't see how to factor it. That's okay. That's what this quadratic formula is for. If you look at this equation right here, you identify what A, B, and C are. A, B, and C are the numbers in front of the x squared, in front of the x, and the constant at the end. So A is 1, B is 3, and C is negative 10. Does everyone see where I'm getting those from? Then you plug them in here. X equals negative 3 plus or minus the square root of b squared minus 4a times c. Notice that when I plug in negative numbers, the inside here, that negative 10, I'm using parentheses. Very important. I'll tell you, a lot of people, even when they memorize the quadratic formula, which you actually don't really have to do, a lot of people, when they memorize the quadratic formula, they don't know how to simplify it. What's 3 squared? 9. What's negative 4 times 1 times negative 10? Positive 40. So this ends up being x equals negative 3 plus or minus the square root of 49 over 2. Do we know what the square root of 49 is?
7.
7. So it's negative 3 plus or minus 7 over 2. That means that our zeros are negative 3 plus 7 over 2 and negative 3 minus 7 over 2. Can we simplify those?
Yes.
What's negative 3 plus 7? Negative 3 plus 7. 4. 4 divided by 2 is 2. That's okay. It's hard to think on your feet when Steve's staring at you. Negative 3 minus 7 is negative 10. Divided by 2 is negative 5. Did we get the same answers
Yes.
that we got when we factored? Yeah, that's the whole point. Now, if you can see how to factor it, is factoring quicker?
Yeah.
Yes, but will the quadratic formula always work? Always, every single time. And sometimes we need to use it because maybe we can't see how to factor, or factoring just can't be done. So let's try the quadratic formula again. And this time, we will find the zeros for x squared plus 2x minus 10. Now, I am not going to claim that it's impossible to factor this, but I will tell you that in order to factor this, you do need to use irrational numbers. So I would say that even if you're a mathematical genius, and I'm sure some of you are, it's very difficult to factor this one. So we use the quadratic formula. A equals 1, B equals 2. What am I talking about? You're all mathematical geniuses. You're taking algebra in college. It's awesome. X equals negative 2 plus or minus 2 squared minus 4 times 1 times negative 10 all over 2 times 1. So that's how you set up the quadratic formula. You plug in your A's, you plug in your B, you plug in your C's, and you get this set up. This is still negative 2. Inside here, this is going to be 40 again, but the 2 squared is 4. So if you'll allow me just to skip a little bit of arithmetic, that's going to end up being a 44 under there. Now, does anyone off the top of their head know the square root of 44? I don't expect you to. I don't either. All right. Now, what I'm going to do, everyone, is I'm going to show you how to properly simplify this, and I'm going to show you all the ways people mess up simplifying this. The proper way to simplify this is to look for a factor of 44 that is a perfect square. 44 is not a perfect square. But is there something you can pull out of 44 that is a perfect square? Well, what are the perfect squares? There's 4, 9, 16, 25, 36, 49. Those are the numbers we know the square root of. Can we pull any of those out of 44, factor any of them out? 4, yeah. We can rewrite this as 4 times 11. Now, some people don't show every little step here, but for the purposes of our lecture, I'm going to show every little step. Square root of 44 can be written as the square root of 4 times 11. Both the 4 and the 11 get their own private square root. And we get that. Some people at this point do this. Everything I'm doing right now is correct, everyone. I'm not making any mistakes right now. Some people would do this. They would pull a 2 out on top. Like that. They'd pull a 2 out, factor a 2 out. Or some people would just go ahead and slash all those 2's like that. Either way, this person's also going to slash the 2's, and they're going to end up with negative 1 plus or minus the square root of 11. And this person's going to end up with negative 1 plus or minus the square root of 11. Either way, you win. How many answers is that? It's 2 answers. The zeros are negative 1 plus the square root of 11, and negative 1 minus the square root of 11. These are real answers, everyone. They're just irrational answers. They're real because did I ever take the square root of a negative? Did I take the square root of a negative? No. Did I take the square root of a nasty number like 11? Yes, but never a negative. Class, this is a tricky concept, this quadratic formula, because people think that all there is to the quadratic formula is memorizing the formula. And they think, once I memorize that, my factoring days are over. Well, it can be trickier than factoring when factoring is possible. And it's not just the plugging in, it's the simplifying that destroys people on these things. Because people get to this point right here. This will be the adventures of mistakes in simplifying. People get to this point right here, and they start doing things they're not allowed to do, like slashing these 2's and saying that the answer is -1 plus or minus the square root of 44. Now we know that's not right. These are all mistakes. Other people say, I'm too clever for that. I know that you have to cancel with everything. So it's going to be -1 plus or minus the square root of 22. Haha, I remember to cancel that with a 2. Can't do that, it's under the radical. To cancel in the quadratic formula, all 3 terms must have the factor and it needs to be outside the square root on that one term. So you needed all 3 of them. 1, 2, 3. All 3 of them to have something if you want to cancel it, and it needs to be outside the square root to cancel it. Otherwise, you're going to get a bad answer. These are wrong. These are wrong over here. Don't do those. Now, you'll get some practice with that when you do your homework, of course. I just wanted to let you know that that's one of the common pitfalls. People try to jump their simplifying too soon, and you can't do it. Steve claims that -1 plus the square root of 11 and -1 minus the square root of 11 are zeros of g of x, x squared plus 2x minus 10. Why? Because the quadratic formula gave me that those were the zeros of this equation. That's what the quadratic formula does. It tells you zeros. That means, class, someone's having more fun than us. That means that if I plug -1 plus the square root of 11 into this function, what should I get as an answer? A 0. Everyone agree with that? A 0 is a number you plug into a function to get a result of 0. So my claim is that if I plug one of these zeros in here, this should simplify to 0. And that looks ludicrous. And in fact, we almost never do this. I'm doing this as an exercise for class. Look at this. My gosh. I'm going to have to FOIL that first thing. So you have to FOIL this thing. So -1 times -1 is 1. -1 times the square root of 11 is minus square root of 11. Square root of 11 times -1 is another minus the square root of 11. And square root of 11 times square root of 11 is 11. Minus 2 plus 2 square root of 11 minus 10. Well, that's what happens if you clear out all the parentheses. Huh. Well, let's see what we have here. I have 1 plus 11, which is 12, minus 2 minus 10. 12 minus 12? Negative square root of 11, negative square root of 11, positive 2 square root of 11. Well, that's negative 2 root 11, plus 2 root 11 equals 0. Isn't that awesome? Who would have thought that such a nasty number would do that? Now, if you want to know what that number is, you get out your calculator and you type in -1 plus the square root of 11. And you'll be looking at a decimal that you don't want to look at anymore, but that represents the number that you plug in here to get a 0. We can't write the decimal as our answer because the decimal goes on forever and ever. It's not exact. But it is a real number. I think that's pretty cool. All right. Why is this especially helpful? Because we can actually find imaginary zeros with the quadratic formula. You're probably not going to be able to factor that, and that's okay. That's okay. Because I remember that the quadratic formula has a job. That is, if someone tells me to find the zeros of a quadratic, like this, then I can use this formula, and it will give me the zeros. Every time, it's perfect. It always works. Always. Even if you could factor it, it still works, as we saw in our first example. So, x equals -4 plus or minus 4 squared minus 4 times 2 times 7 all over 2 times 2. You can actually see, before the formula alarms, you can actually see you're actually only plugging in 5 different places. 1, 2, 3, 4, 5. Then you simplify it. 8 times 7. Does anyone see a big warning flag going off? Yeah, this is going to be a negative with the radical. Everyone see that? 16 minus 56. This ends up being -4 plus or minus square root of -40 over 4. When that happens, a little siren goes off. Good luck to the people just looking at these notes, not listening to my lecture, figuring out what this is supposed to be. But this is a little siren that says we have imaginary numbers coming up. That's okay. Can I cancel this 4 with this -4? No, you can't, but there is a way people kind of wiggle around that. I'm going to show it to you. It's kind of sneaky. What they'll do is they'll do this. They'll break this up into 2 different fractions. And this is also allowed, everyone. I have not done this yet today. They break it up into 2 different fractions like that, where they each get the 4. And now you can rewrite this as -1. But I really don't know what to do with that square root of -40. Well, let me think. Square root of -40 is the same thing as the square root of 40 times -1, or square root of 40 times I. In fact, anytime you have the square root of a negative number, class, you can just rewrite it as the square root of a positive number with the I on the outside. The I is on the outside. Does anyone know the square root of 40 off the top of their head? Does anyone know 2 numbers that multiply to 40 where they know the square root of one of those numbers? 4. So this is 4 times 10, or 2 root 10 I. That takes a little bit of practice, simplifying those numbers. So this is 2 times the square root of 10 I over 4. So I can cancel that a little bit. Like that. And I'm allowed to do it individually because I broke it up into 2 different fractions. If you look back at the previous example I did not break that one up into 2 fractions. What's my claim, everyone? My claim is this. G of x equals 2x squared plus 4x plus 7 has two zeros. -1 plus the square root of 10 over 2I, and -1 plus the square root of 10. Oops, I wrote the same answer twice. This one has a minus. By the way, square root of 10 over 2I is the same thing as square root of 10I all over 2, as long as the I is outside the radical. So, we got two imaginary zeros. What makes them imaginary? I took the square root of what kind of number? A negative. Imaginary zeros of quadratics always come in what we call conjugate pairs. In conjugate pairs. You see, if you look at those imaginary numbers, -1 plus the square root of 10 over 2I and -1 minus the square root of 10 over 2I, you will see they actually follow the formula that we said complex numbers had to follow, which is A plus BI. So check this out. Is that what I want to say? Let's actually keep it like this. Every complex number that is not real has a complex conjugate. A complex conjugate is simply the complex number where you change the sign on the imaginary part. In other words, 2 plus 3i, 2 minus 3i. -12 plus square root of 7i, -12 minus the square root of 7i. These are called complex conjugates, everyone. And every complex number has a complex conjugate, and, reiterating, if the zeros of a quadratic are imaginary, they are complex conjugates. G of x equals 2x squared plus 4x plus 7 had zeros that were -1 plus the square root of 10 over 2i and -1 minus the square root of 10 over 2i. They always come in those conjugate pairs.
So they should be answered that way.
Well, what I'm kind of saying is if you know one, you know the other one. Yeah, and when you give your answer, you can use the plus minus symbol. That's okay, as long as you realize that you are giving two different answers. That's the main reason as I said before, I don't like the plus minus symbol. I think it's a great symbol. I think it saves time. But I think sometimes when people write that, they forget they're actually getting two different answers at the same time. That's why I try to avoid it when I'm lecturing. All right. This does not apply to rational numbers. This does not apply to rational numbers. So if 4 is a 0, that does not mean that the other 0 is negative 4. This does not mean that they're always plus and minus. In Math 121, it does apply to irrational zeros. 1 second, class. Just need to grab some of my notes here. Where were you? There you are. What do I want to say here? I want to say irrational numbers have conjugates too. So here's the punchline. I know I got kind of bogged down there and I was kind of talking myself into a slump, but let me say this. We're trying to find zeros of quadratics. When they're imaginary, or they're irrational, meaning they have this square root that won't go away, they come in pairs. All right. Now we're going to get really deep into this chapter. Chapter 3 goes on for quite a while, and we're going to see a lot of different cool math happen. But one thing that we want to remember is what we're doing when we find a zero. So, what does it mean to say -1 plus the square root of 10 over 2i is a zero of g of x equals 2x squared plus 4x plus 7. What does it mean when I say that's a zero of that? What am I talking about?
So if you put 0 back into the equation, it's going to equal, not 0, if you put a -1 blah back into the equation, it's going to equal 0.
If you put blah, I like it, back into this equation, you're going to get 0 as an answer. Now, that's important for us to remember because we're not always going to check these. We're going to trust that we did it right because even someone who really enjoys doing math is probably not going to say this is their favorite math to do right here. But I kid you not, everyone, this mess plugged into this equation will simplify down to the number 0. And I'm going to show you that. So you'll remember that that's what a 0 is. Whether it's the number 2 that makes an equation go to 0, or it's the number -1 plus the square root of 10 over 2i that makes it go to 0, this will make this go to 0. Now, this is a good exercise in learning how to work with these imaginary numbers a little bit, because look at this. I have to foil this thing. And this is actually the hardest part of the whole process, is foiling that, because it has a squared on it. What's -1 times -1? Okay, you do the rest. No, I'm just kidding. All right. So, oops, forgot my I. Almost blew the whole deal right there. All right, square root of 10 over 2i times square root of 10 over 2i. You know what? I'm in no mood to even do that right now. I'm just going to, not going to even try to do that in my head. That sounds like a nightmare. I'm just going to do that and write it and then take care of it in a second. This one and this one, I get minus square root of 10 over 2i minus another square root of 10 over 2i. Well, that's how you foil it. It's not simplified yet, but that's how you foil it. Okay, well, let's leave that alone. That takes care of this part, except I need to multiply everything by 2. Holy cow. And this should not have a squared on it. Good, Stephen. So, we're going to finish this problem together, but you see why we don't do this very often. But what is this supposed to equal when I'm done?
0.
There's no way. There is just no way. All right, let's see what we got here. I guess I better do a little simplifying here. So this is going to be 1. If I add these two together, all right, think about this, everyone. If you add two fractions together that both have a 2 on the bottom, that's like adding two halves together. Everyone agree with that?
Yeah.
So this should just become square root of 10i when you add them together. And this should become minus square root of 10i.
No, you're not adding, you're multiplying.
Yes. Yes, I am. Right, we multiply these. We get 10, 4. You know, I'm glad you said that because I was about to wonder what just happened. All right, these two I'm basically adding. They're both negatives. I'm sorry, I got my so this is minus square root of 10i. That's what happens with those. This ends up being square root of 10 times square root of 10 is 10. 2 times 2 is 4. I times I is I squared. We're solid. What did I say before? Even people that like math don't do these very often. So what we got now? Let's distribute the 2. That's going to become 2 plus 5. What's I squared? Negative 1. Okay. Minus 2 root 10i minus 4 plus 2 root 10i plus 7. 2 minus 5 is negative 3. Minus 4 is negative 7. Plus 7. Negative 2 root 10. Holy cow. Isn't that wicked? So please, don't forget, when you find a 0, whether or not you are saying that 2 is the 0 of h of x equals 4x minus 8. Is it, by the way? Is 2 the 0 of that equation? Whether you're saying that because you know that h of 2 equals 0, or you're saying that this, negative 1 plus square root of 10 over 2i is the 0 of this equation right here, you are saying you have found a number that when plugged into that equation gives you a result of 0. What else can the quadratic formula do? Well, check this out. B squared minus 4ac. That's the part under the radical. That actually is very interesting because that's what tells me if I'm going to have a negative, if I'm going to end up taking the square root of a negative. Does everyone agree with that? So there's actually something that people say about this, and it's so important. They actually call this the discriminant, which I can never remember how to spell, so we'll just go with that. That's called the discriminant, everyone. And people actually came up with a little set of rules for that. They said this. They said, you know, if b squared minus 4ac is negative, if that ends up being negative, we will get 2 imaginary zeros which are conjugates of each other. In other words, they'll both be nasty imaginary numbers, but we'll have a plus, we'll have a minus. Then they made the observation that if b squared minus 4ac is 0, if that just ends up being 0, the square root and plus minus goes away, and you get one real answer. You're only going to get one answer if that whole square root goes away. Just one answer to the problem. If b squared minus 4ac is positive and a perfect square, get two rational answers. If b squared minus 4ac is positive and not a perfect square, you get two irrational answers, which are conjugates of each other. You get something like 2 plus the square root of 3 and 2 minus the square root of 3. Still real, just irrational. So the very last thing I need to mention today, and I only have a few minutes left, and that's why I say this for the end, is because why does the quadratic formula work? And I got a really big picture here. It's not even a picture, it's just something I didn't want to have to do for you. I guess my other question is, where does it come from? You don't need to bother copying this down. Not only on post after class, but you're not going to have to repeat this process. But here's what happened. Someone took the most general quadratic they could, ax squared plus bx plus c, and they said, I don't know anything about this except I know that there are some numbers in there. And what they did was they solved it for x. Now, I used to do this for classes, but it took like 10 minutes to do it, and I didn't test people on it, and I was exhausted. And the only thing I got out of it was a round of applause, which was awesome. But I mean, what happened is someone took this thing and they actually solved it for x. And they ran through this whole process. They set it equal to 0, right up here. Now, is that how we find zeros, everyone? We set an equation equal to 0 and solve for x? Then they used this process and they solved it. And they ended up with the quadratic formula, using a process called completing the square. In C's class, you will want to know the quadratic formula. It will help you with your homework. And I'm going to learn you how to, I'm going to learn you. Good. Welcome to college, everyone. I'm going to help you learn. You will learn. I will teach. I will teach you how to do this thing called completing the square without all these symbols. I'm going to teach you how to do it with actual numbers. But it's a process that will help you avoid having to memorize or simplify the quadratic formula. So, next time, we will learn how to complete the square to find zeros. Class, real quick before you go.